All right, good afternoon. It's time once again for Organic Chemistry with your host, me, Dr. White, who's sort of running on only a couple cylinders, but I'm running, and that's the important thing. And I'm feeling better now. See what organic chemistry and nice people do to me. All right, what I'd like to do today is, as I promised, I'll go through the problem set for the ethers and epoxides. Then we'll finish up the ketones, aldehydes, and then we'll do the lab. And if I'm still breathing, I hope no. But anyways, I think I'll go back and do a couple of ketone reactions again that will help you. So let's get going. Remember, if you have any questions, ask away. If we look at the ethers and epoxides reaction problems, the first one, what do we have that's different? Now, as always, especially in this chapter and the ones before, and the one we're doing now, and the later ones too, look at an organic molecule, look for what's different. What's not a carbon-carbon single bond, and more importantly, what's not carbon or hydrogen, should get your attention like that, like that. And if we look here, we see an oxygen, that's not carbon or hydrogen, with negative charge sodium cation, and this is called an alkoxide, which I won't ask you, but you should know. And what's different here? Carbon, hydrogen, halogen on a carbon, that's different. And that should be a prime up there, it fell off. And this is the Williamson ether synthesis. The alkoxide attacks, organic chemists are violent, if you don't know. The carbon with the halogen kicks it out, and this oxygen bonds to the carbon with the halogen. Well, in this case, it's the N carbon of 3 carbons. So what's my R? Methyl. What's my R prime? N propyl. Methyl, oxygen. Which carbon has the halogen of these 3 carbons? The N one, and that's why this is there. Let's do the next one. Ooh, a ring. Dr. White loves rings, but that's carbon hydrogen. Here we have oxygen minus sodium cation attached to carbon, alkoxide, alkyl halide, carbon halogen, and I'll call this ring R. This 3 carbons R prime. Notice the halogen is on the center carbon, and therefore this attacks that. And notice you have the ring, bond to an oxygen, and then the carbon that's bond to oxygen is the center one. You put it on the N one, like students do, O, CH3, CH, CH3, that's wrong, and I mark it as such. And this is the same one. And here, if you notice, R and R prime are the same, and we make probably the most famous ether of all, diethyl ether. You notice I didn't put any problems down for nomenclature. Can you keep a secret? I usually don't put ether nomenclature on a test or final. Shh. Hopefully nobody will hear this. But anyways, I don't. Now, let's look at the next first of all, before I move on. Anybody have any questions about ethers? How to make them? Well, let's move on. Now here, let's look at what's different. And if we look here, we see carbon, 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 hydroxyl group on a carbon, alcohol. Ooh, this is different. An oxygen in a 3-membered ring, 1 oxygen, 2 carbons. This is an epoxide, the only one I'll ask you to learn, ethylene oxide, alcohol, ethylene oxide. This oxygen bonds to this carbon. This hydrogen, you break this carbon-oxygen bond. This hydrogen goes to the oxygenator to form an alcohol, and you make this ether alcohol. In this case, R is 4 carbons. The carbon with the hydroxyl group is the carbon this oxygen of the ether in the ether alcohol will bond to. And if we look here, I did the chemistry instructor's favorite trick on a test. I put a big, scary R group. No, it's just what's different, carbon with a hydroxyl group, alcohol. R happens to be big and not scary if you know what you're looking at. And then again, 3-ring, membered ring, oxygen, 2 carbons, ethylene oxide. I'll never ask you what ethylene oxide is, same thing. This is R, oxygen, CH2, CH2OH. And here for some overkill, I have this one in F. Now I got a really big R group, but what's different? Carbon and a hydroxyl group, alcohol, which is way up here. And now ethylene oxide, ether alcohol, what's R? This whole big thing I have circled. The carbon with the hydroxyl group will be bonded to an oxygen, CH2, CH2OH. Ooh, we've got a dilemma here on G. We've got 2 functional groups. I've got an aromatic ring and an alcohol, carbon with hydroxyl group. This is phenol. Hopefully you know that name. And that's the common and the IUPAC name for this alcohol. We did that in alcohols. And number 9, and ethylene oxide. This is a reaction of alcohol with N moles of ethylene oxide. Ethylene oxide will not react with a benzene ring, so this is just a big R group. And therefore you get this polyether alcohol, R, benzene ring, OCH2, CH2 in the brackets, what's N, 9, and outside hydroxyl group. Now, common mistake, students put the hydroxyl group inside, and I mark it wrong. I'll say it again. Common mistake, students put the hydroxyl group inside the brackets. Don't, because it's not correct. And here I give you another one. What's R? 4 carbons. N is 5, ethylene oxide. You have CH2, 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 our R group, then bonded to this polyether. That's what the brackets and the 5 subscript here tell you. O, CH2, CH2, and outside the bracket is the hydroxyl group. Now, on test 2, similar, but a little different than test 1, I will have not 1, but 3 synthesis problems. Any more would be cruel, unusual against a student, and I can't do that. And this is synthesis. I'll be nice. This shows you react 2 organic molecules to make this organic molecule. Ooh, this is different. A salt, sodium bromide. What is this? Remember we played that fun game, circle and name the functional group. You should know this is an ether. I have my R prime, ether. And sodium bromide is my salt. How do you make an ether? An alkoxide plus an alkyl halide. What's X? Well, I tell you, bromate. And if I call this R and this R prime, the carbon with the oxygen here is the carbon with the alkoxide here, and the carbon with the oxygen here in R prime would be the one that has the halogen here. Now you can say, no, let me call this R prime, this R. If I do that, R is CH2, CH3, which carbon has the oxygen here, has the oxygen minus Na plus. By the way, if you don't want to put charges, that's okay. Dr. White likes to. And the other side gets the halogen. There's only one carbon, that's that. All right, let's look at this one. Again, you have two starting materials or reactants. And what do we have here? Ooh, 3 carbons, oxygen, another 3 carbons. This is an ether. Ooh, sodium iodide is salt. How do you make an ether? Williamson ether synthesis. I can call this side R and this side R prime. If I do that, this carbon has an oxygen with a minus charge. Ooh, it does. And this one, which is an isopropyl group, the carbon, the center carbon of 3 carbons has the oxygen, and that will have the halogen, R prime, which is iodine. Now I could have said, no, I'll make this R prime, and I'll make this isopropyl group R. Well, if I do that, then I have R is these 3 carbons, which carbon has the oxygen, the center one, and it will have O minus Na plus. These 3 carbons, which one has the oxygen, the end one, and that will have the halogen, in this case, iodine. Now, Dr. White made a big mistake, and that is on this problem C. Cross it off, because I'll never give you an ethoxide reaction, and that's what this is called, reacting ethylene oxide with an alcohol, whether 1 or 4, and there should be a 4 in front of there, but since I'm only asking what are the starting materials, they actually don't need the 4, which is but this C, just cross off. All right, any questions? All right, yes.
Is this worksheet under assignments?
I'll have to put it up.
Okay, because I didn't see it up there.
It's been a rough morning. I didn't get to do the labs I should have graded this morning either. So,
it's okay.
Alondra, thank you very much. I will do that so you can get your 1 point.
Thank you.
Oh, that wasn't too bad. To my back, reaching for my writing tablet. Check something out. Remember on Monday, I was having problems with my writing tablet, which I just call my whiteboard. And what I did was a standard trick when you're trying to fix some problem with computer peripherals, take all the plugs out and put them in. And the other thing, which I also did at the same time, which I don't know which fixed it, but one of them, I rebooted that computer. Now, I didn't want to do that while you were online, because if I rebooted a computer, I would have killed the session. Then I'd have to start a new one, send you a password. So hopefully you didn't mind putting up with that disgusting lines on the tablet. All right, let me check. Everybody see Keto, Tautomerism? Thank you. All right, next couple of slides, I'm going to turn the switch. Is this on a test to the off position? but it will give you background information to understand the reaction that will be on the test. Now, I should tell you, if I look, even though I'm in some back pain, like I mentioned earlier, but I'm smiling heavily, I am, because you're in hallowed ground, because this is the area that I'm a world expert on, and this is the area I did my PhD thesis on, a very specific area, part of this. And this deals with ketones and aldehydes. And the first thing I want to teach you is something called a keto enol tautomerism. Now, I'll never ask you on a test, but tautomerism is two different molecules that differ by just their placement of electrons and atoms. They're not true isomers per se. I guess you'd call it an isomer, but it's called tautomerism. I don't know what the word tautomer stands for, but I've always used it because organic chemist. What does this mean? Let me check. Everybody see the whiteboard now? Thank you. Again, this you don't have to write down, but this is a ketone or aldehyde. And if R prime is H, it's an aldehyde. If it's carbons, it's a ketone. Now, the carbon bonded to the carbonyl carbon has a special name. Again, switches off. And that's called the alpha carbon. Dr. White loves alpha carbons. And turns out there's a tautomerism. I don't even think you really call it this. Well, I guess you do this for tautomerism, where the following happens. And notice the electrons here go there, and one of the hydrogens goes to the oxygen. And this is what you get. Now, this is called the keto form, because the ketone, or it could be an aldehyde. Why they don't call it the aldol form? Well, I know why, and I'll explain later on why, at least I think I do. And this has a double bond, so we call that ene, like en, the ending. This has an alcohol, and we call that OL, and this is called the enol form. So this is a keto enol tautomerism. And because this happens, that has tremendous implications for the hydrogens on the alpha carbon. And these are called the alpha hydrogens. And turns out, unlike normal hydrogens on a carbon, the hydrogens on the alpha carbon to ketone or aldehyde are special. Oh, are they special? And turns out the alpha hydrogens in a carbonyl compound, ketone or aldehyde, are more acidic than hydrogens on an alkane carbon like CH2, CH2, etc. And the reason is resonance stabilization of what we now call the enolate anion. Again, switches off here, and Dr. White's feeling 100% better because I'm talking about halo, very sacred area of organic chemistry. And let's do the same thing. Let's look at this carbon. the alpha carbons and these hydrogens, and think of it as an acid-base equilibrium. Now I am using the two arrows correctly. And if this were to lose a proton here, which is what acids are, proton donor, I'd get this enolate anion. And I can draw a resonance form. A resonance form is where you're only moving electrons. So if I move the electrons here, these will go here. And therefore, I'm going to use correctly the double-headed arrow now. And these are the two resonance forms of the enolate anion. And when you can draw more resonance forms of a molecule, it's more stable. Now, if I were just take an alkane, I probably should make this arrow like even tinier. This is called the carbanion. It's probably the strongest base in the world because it doesn't want to do that. In fact, you got to really work hard to do that by treating it with a very, 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 two more very strong base. And why? Because I can't draw any other resonance forms, and carbon doesn't like a negative charge. But you say, well, Dr. White, it's got one up here, but it can also have this resonance form, and oxygen is always happy because it's more electronegative to get a negative charge on it, extra electrons. So this is the enolate anion. Now, what that means is with an enolate, with a ketone or aldehyde, I can react this with a base and make the enolate anion whenever I want. And the enolate anions are very, very, very special. How special? Well, I'm going to show you. Wrong one. Right one. And what I'm going to show you now, switches on, is the aldol condensation. And the aldol condensation, you make an enolate anion, and it acts as a carbon nucleophile. Now, I'm going to rewrite this, so don't write this one down. Actually, I'll do it underneath. Now, you can do this with ketones, but my gift to you today is, for this semester, and I always do this, I'm only going to talk about aldehydes. And another gift, wow, I'm giving you guys a lot. Don't tell anybody I'm being so nice to you. It'll ruin my image around here. When I put on the test, I'll put both the same aldehyde. If I were talking to other PhD chemists, I'd just put the one in black, and I may or may not put a 2 in front. Usually you don't because everybody knows this reaction. But here, I'm reacting with sodium hydroxide. I don't have on the slide here. You probably have a solvent, water or alcohol. And what happens is, and I'll explain this in a second with the mechanism because Dr. White wants, This forms the enolate anion on this carbon. That's what this does. The carbon enolate anion is a good nucleophile. What's the nucleophile? Something looking for a positive charge. As I mentioned earlier, the carbonyl carbon of a ketone and aldehyde has a slight positive charge. Therefore, anything looking for a positive charge is going to attack that carbon and bond to it. And guess what? It does. So this attacks that carbon, opens it up, because you can't have more than 4 bonds to carbon. You're going to lose 1 hydrogen there. Let me whoa, come. Let's try this again. There. Now, notice I've lost 1 hydrogen from the first aldehyde. Everything else stays the same because you don't break carbon-carbon single bonds. And then it bonds to this carbon, the other carbonyl carbon, and opens it up to an alcohol. What's attached to that is still attached to it. And you've made this new molecule. And the most important thing, the beautiful thing about enolates anions are, it allows you to make a new carbon-carbon single bond. And that's always very special, and that's always so important to be able to do. In fact, half the reactions of the 10 or so I know where you can make a carbon-carbon single bond involve enolate anions. This is the only one I'll be teaching you this semester because this is a 1-semester course. If we're a 2-semester chemistry major course, there's 1 or 2 more I teach you, and then at my level, I know even more. That if this were a PhD course, I'd teach you more. All right, now, why is this called the Aldol condensation? Condensation, condense, bring 2 things together, and notice right here, I have an aldehyde. And notice right here, I have an alcohol. And somebody got real cute and said, let's take this part and let's take this part, put them together because they're in the same molecule, and we'll call this an aldol. Isn't that cute? And that's why we call this the aldol condensation. Now you can use other bases. I'm going to stick to sodium hydroxide. And the question is, what's the organic product or product for the following? And if we look at this, what's different? Ooh, an aldehyde. And because I see the same molecule twice, the same aldehyde, I'm going to write it this way. If we look here, ooh, base and aldehyde, alpha hydrogen, carbon, and you remove an alpha hydrogen. I can do that. I'm going to move it up over here because I need more room. See how from the alpha hydrogen, I took one hydrogen off because it's going to bond to this carbon right here. And you've made that carbon-carbon single bond. And what's attached to this carbon right here is still attached to it. And in our case, what's our methyl? And now we have this right here, and I'm going to remove one carbon hydrogen from the alpha carbon. And then this carbon here will open up to an alcohol. And what's attached to it is still attached to it. Now, students forget this carbon, CH2. Remember, all this is coming along for the ride. And another thing is they forget to make this an alcohol. And what you see on the paper when you're grading is something like this. If you notice this carbon, there's something wrong. What's wrong? It's got 1, 2, 3, plus 4, it's a double bond, plus 5 bonds to carbon. No. Remember, there's only 4 bonds to carbon. So I'm going to let you try one too. Good news, I'll never put a synthesis problem involving this reaction on a test or final. That's cruel, unusual punishment. And I think it's still outlawed, at least today it is by our Supreme Court. Next year, I don't know, but now, no. All right. Remember when you're done, give me a thumbs up or smile. All right, let's do this. And if I look at this reaction, what's different? Ooh, an aldehyde, another aldehyde. Remember, carbon, oxygen, double bond with R, in this case, R prime is hydrogen. Could be a ketone, but I won't put that on test because that makes it more interesting. And here I have R group. Well, I could call it R, but they're two of the same aldehyde. This is an aldol condensation. Why? Because I'm reacting with sodium hydroxide and water. If I write two of the same aldehyde this way, remember the alpha carbon has hydrogens you can pull off with a base and forms the enolate anion, and this attacks the other aldehyde. And if I look at this, I'll write the first aldehyde where I've removed one of the hydrogens, the alpha carbon, and then this one right here, this carbon, I'll open it up to an alcohol, put my hydrogen, whatever else is attached to it, because you don't break carbon-carbon single bonds. Now, if we look at our specific example, here's my alpha carbon, here's the hydrogens on there, the alpha hydrogens. I'll call this R, same thing here. Now you can either memorize it or remember, this is going to attack the carbonyl carbon. So I'm going to draw this first, minus one hydrogen here. Notice I've taken off one hydrogen. Instead of two, there's one. And then underneath, I'm going to draw this carbon right here. And I'm making that special thing, a carbon-carbon single bond. And this opens up to an alcohol. What's attached to it? H and three carbons, my CH2, and then my R group, CH3, and CH2. And notice starting with a very simple little aldehyde, I've made a very, very complex big molecule that I can use to make other things. And it now has, instead of 4 carbons, it's now much bigger with 8. And that's the aldol. Oh, let's do one more. These are fun. These are good for my back. And by the way, this is a cyclohexane ring, not a benzene ring. It could have been a benzene ring, but I didn't want to confuse you too much. Have fun. Well, everybody done? I guess that's the new thing. Put your knee up when you're done. My eyes are still working. Thank you. All right, let's do this. If I look at this, I say, what's different? Oh, look, carbonyl hydrogen carbons and aldehyde. And it's the same one, second molecule, same one. Immediately reacting it with base tells me this is an aldol condensation. Dr. White loves aldol condensations. Hint. And if I react the same aldehyde with itself in the presence of sodium hydroxide, a base and water, the alpha carbon has acidic hydrogens that I can pull off with a base to form the enolate anion. I just did that. And this alpha carbon, the enolate anion, with the negative charge on that carbon when it's in that form, resonance form, attacks the carbonyl carbon of the other aldehyde, opens it up to an alcohol, and what's attached to it is still attached to it. And you made an aldol. Whoa, that's better. And now if we look at here, this is my R group, a ring. So I'm going to take the alpha carbon, remove one of the hydrogens. Everything else stays the same. And it attacks this carbon here, which opens up to an alcohol, and everything else is still attached to it. And that's the molecule. And notice a simple aldehyde, you've made a really, really complex molecule in one simple step. And that's the beauty of enolate anions, in this case, the aldol condensation. Now, I'm going to bring back an old memory, a good friend of mine, and that is what I'm going to tell you. Most organic chemists wouldn't even understand what I'm about to say. Dr. White did his PhD thesis on kinetically favored cross-conjugated enolate anions. Oh, that makes me feel so warm and good inside. And it was a real adventure to work with my professor, Dr. Roosh. That was the area he'd been investigating for a long time, enolate anions, and that one in particular, and the special molecules you could make by a certain reaction, which I'm not going to teach in this class, called the Michael reaction. And I did that, and I made very complex ketones from that. Did more stuff after the actual enolate reaction. But enolate anions are my friend, have been for many, 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 many years. And in fact, my last patent, US patent, I used an enolate anion in a way nobody else had ever done to make a new resin. That's a fancy way of saying a glue that holds sand together that makes molds to make things like your car engine. Now, I don't know if you can see right up there. I'm not going to get up because my back is still killing me a little. You'll see a little black thing with two stones in it next to my favorite picture from my favorite movie, Forbidden Planet. I got this on eBay a while ago. Someone was selling it. I've got 2 different copies of the movie. In fact, I've been watching that movie since I was 8. I can probably do the whole movie, every line by heart by now. It's a great movie. But this is called a dog bone, where you use to make, without the stones in there, I made that specially, but to test the strength of a glue or resin for mold, because this is made out of sand, and you pull it apart with a machine. Now, the enolate anion I used to make a special type of resin that was very low polluting resin, because afterward, when you pour the hot metal into the mold, eventually all that burns off into the air. And if it's not made correctly, it can be very stinky and polluting. And if you have polluting, if you ever go by a foundry, a lot of them don't smell well because they're burning off the glue. If you've ever smelled glue, or at one time they used protein from horses. This was back in the late 1800s, 1900, and it really reeked. If you've ever smelled something burn on a barbecue, that's what it smells like, but worse. And like I said, my use of an enolate anion allowed me to do stuff, make a resin that was very low polluting, low odor. In fact, one of my fond memories was one of the companies that used that new resin, Ford Motor Company, and it was in their Windsor foundry in Windsor, Canada. They personally invited me, the manager, their foundry manager, to thank me and also see their foundry, which was quite an honor. The foundry was much bigger than Elgin Community College. And that was just to make, and the day I went there, they were making V8 engines for Ford cars. And one of the things, the memories was in their quality control, how they test they're making good engines. Every once in a while, I don't know how many hundred, when they have a new glue they're testing or other things, they take an engine that was already made, pull it off the line where they were making it, and then here's this huge car engine. And with saws, they cut slices. So the whole engine was pieces this big, and each slice was a lot of weight. And I asked the guy, well, I wish I could take one of those home. He said, how are you going to get that on a plane? And I said, yeah, it weighs a couple 100 pounds. You know, can you ship it to me? And they laughed. But I got some good pictures and nice memories. All right. Now, if I look at the clock, and because of my back, instead of taking a 5-minute break, I'm going to go and let's do the lab now. I'll get you out in about 10 minutes or so. You get out early, I get out early. We're ahead of schedule, so everybody's doing well. And I can go do my back again. One of the tricks I learned from last year from physical therapy I took, because I was having problems with my leg and foot, and turned out it was really my hips that were causing the problem, was when you have muscles that lock up, besides just rubbing them, a good way is, which I actually went out and bought one because I didn't have it, I'm not going to use it now, is you take a rolling pin and rub it up and down the muscles, and that loosens them up. Plus my heating pad helps too, and a couple of aspirin. Luckily I don't have to go to heavy stuff. Now, bear with me because I was running late and I didn't put the, that's not what I want. That's what I want. The lab is on another machine. I have 3 PCs I use in my office. And this one I use exclusively for Zoom and some other things. In case you wondered, this picture up here is a condenser, like one I used in grad school. When we get to distillation lab, I'll explain more. Tell me I can't do this. I can. Again, normally I transfer files over to this one by using, I don't want them hooked together in a network, so I use a thumb drive. And this morning or today I was running way late, so I didn't. Let's do this. Success. Hang in while I do something. Log off. Two days later, all right, everybody see the alcohols lab? Thank you. All right, let's get your safety goggles on and go to lab. Today's lab will be the alcohols lab. And remember, alcohols have this structure. Remember, don't forget to turn the lab that's due today, and this lab will be due next week. Now, the first thing, and what I've done in these labs, if we were at ECC, is have you do some very important but hands-on for alcohols. And the first one is solubility of alcohols. And you'll determine the effect of branching and carbon length on solubility of alcohols. Now, alcohols, oh, that's not what I want. Are slightly polarized. That means little delta, slight charge. If you notice, water is polarized too. And because of that, alcohols can hydrogen bond. That's called a hydrogen bond, abbreviated by H. And that helps in the solubility of alcohols in water. By the way, don't tell bartender that when you're at a bar. Do you know why you can make those mixed drinks for me? Because alcohol is hydrogen bonding to the water. They don't like hearing chemistry when they're working, and probably when they're not working either. Now, this is a very slight force. And if this gets large enough, will that affect it? If it's branched, will it affect it? Well, I'm not going to tell you. And today's lab, if you had been in the lab today, you take some small test tubes, put some DI water. DI stands for deionized. The ions that are normally in tap water in a laboratory can be removed by a special filter, and we call that DI or deionized water. And you fill up the test tube, you add some of the alcohol, small amount, you're going to test, then you mix it. Then I've got a whole bunch of them for you to test. Now, since you're not going to do this, I have a YouTube video I found, nice one too, for you to see the effect. In fact, when I was watching the YouTube, the next time I'll do this lab at ECC, I'll rewrite it because they add blue food coloring, which allows you to even see the difference if it's soluble or not, even better than the way I do it. So this has been a good thing. So watch this. And if you see two layers, it's not soluble. If you see one layer, it's homogeneous, the same throughout, it's soluble. Now, if we were in the lab, I'd give you this table and you'd go in the lab and mix this these alcohols with water and see if it's soluble or not. Now, we're not going to do that because I don't think you have these at home. I'm sure you don't have 1-octanol at home, and you probably don't have T-butyl alcohol, otherwise known tert-butyl, 2-methyl 2-propanol. So I've given you the results. This one's soluble, soluble, insoluble, insoluble, insoluble. Now, one other thing on this table, this for this table 1, you don't have to do for the others, draw underneath the structure of ethylene glycol, which is a common name. These are all isopropyl alcohol or 2-propanol, tert-butyl alcohol, 2-hexanol, 1-octanol. That'll help you answering the questions. All right, now another thing which I can't do and a YouTube isn't going to help is I have students smell the alcohols and see if there's a difference in structure and odor. But since we're not going to do that, I just omitted it and I took out the questions. Now, part 3, oxidation of alcohols. Now, let's go to my whiteboard. That's not my whiteboard. There we go. And if we're in the lab, actually, we call it the dry lab. Before we go into the actual lab, I'd be writing this on the whiteboard in the lab. And here, this is a primary alcohol. This is a secondary alcohol. This is a tertiary alcohol. And what we're going to be using is I think this is the right structure for sodium dichromate. I sometimes write it wrong. Now, this is an oxidizing agent, just like if I had written on this, on the test, O bracket like this. And this is an oxidizing reagent. Now, it turns out this has a red or a red-brown, red-orange. My sisters tell me I don't know my colors. I know red, green, blue, but others, they're right. And when you take a primary alcohol, this is oxidized, which we went through this reaction, but I didn't show you specific, and you form an aldehyde. Well, you form something else. This is an oxidizing reagent. It gets reduced, and I'll just do this to this chromium plus 3 ions. This, depending on the concentration of how many drops you put in your solution when you oxidize it, can be either blue, blue-green, almost a turquoise, or a green color. If I can spell green right. And if you take an alcohol and react it with sodium dichromate, and you usually use acid and water, it's called acidic sodium dichromate solution, and acid helps it go quicker, and it's a catalyst. You get this, but visually, if you see a color change, you know you had an alcohol. Now, if you take a secondary alcohol, This oxidizes to a ketone, plus you get the same reduction of the chromium, sodium dichromate to chromium +3, so you'll see that same color change. But if you take a tertiary, which I drew wrong, you can tell Dr. White's a little under the weather. Well, at least I caught it. And if you take this, you get no reaction. And because of that, you'll see no color change. So this is an excellent way to determining, do you have a primary or secondary alcohol, or do you have a tertiary? If you see a color change, you have a primary or secondary. No color change, you have a tertiary alcohol. And what I'd be telling you if we were in the lab right now is, this is where I would say, and you're going to find out, is Dr. White lying to you about that or not? Because you're going to go into the laboratory and prove if I'm right or wrong. I'm not lying, but it still impresses the important part of organic chemistry is a science, and we prove things in the lab. We just don't make it up. And therefore, based on what I just showed you, you'll be doing the oxidation. You put a small amount of the alcohol in each of a number of test tubes. You'll put in about 10 drops of the aqueous acidic potassium dichromate solution. You'll mix it, let it sit for a while, and observe what you have. Now, because there's acid, and I'll teach you later on, reacts with your skin, we wear gloves and always wear eye protection. And since you're not going to do this, here is the alcohols. You've already drawn the structures from table 1, so you don't have to put it here. And here's the results you would see. And you'll use this results to answer questions at the end of the lab. Finally, the last part, alcohols can react with sodium. And here I have, oh, by the way, up here, I found a really nice YouTube for you to watch. Please watch these. They're only a couple minutes at length, and it will show you what you would have seen in the lab if we were in the lab. And now let's talk about the reaction of alcohols with sodium. Now, this is one I didn't talk about in the class lecture part, but you'll see where this is an important reaction. And I'm going to do something very rare. I'm going to balance it. Students get upset if I don't balance it. If you take an alcohol and sodium metal, and I've got a YouTube up here for you to watch. This I actually do as a demo. Sodium is a little too dangerous to let students handle at this point in your career. And it forms what we call an alkoxide. You've seen that, plus hydrogen gas. The G tells you it's a gas. The arrow tells you it's given off as bubbles, and you make an alkoxide. Now, it turns out alkoxides are very strong bases. Hang in there, I'm almost done. And if you remember from your undergraduate chemistry, general chemistry, we have pH, which is a measure of acidity or basicity. pH goes from 0 to 14. If it's above 7, we call that a basic solution. If it's below 7, it's acidic. And the greater the number, the more basic it is, the smaller, the more acidic. So you're going to find out in this lab, you'd see me do this. I take the alcohol water with pH paper, as paper that turns a certain color for a certain pH, and you'd find out the solution is about 7. Now, when I reacted with the alcohol, and the alcohol I would use, the safest one, is isopropyl alcohol or 2-propanol. And it's important you remember this. I have it here too. After you add that, what you do is you add the sodium to that, and then you take some of that solution and put it in water, and now the pH is 13. Now, I'm not going to give away if it's more acidic or more basic. And that's the lab. And again, I have a nice YouTube video right here for you to watch. And here I have questions, and please use your experimental results to justify your answers. And I have part 1 question, part 3 I have 2 questions, and part 4 I have 2 questions. And that's the lab today. And I'm done for today. Oh, wait. Can you guys hang in there for about 5 more minutes? Well, can you? I usually like to take a break, but with my back, I ain't going. Afterward, I'm gonna go vegetate in front of the television set for the rest of the afternoon because I'm caught up except for the labs, and I'll do that tomorrow. I apologize, I'm not getting your labs back. All right. Let me put up what I was just drawing. Notice here, this is a general reaction for a Grignard reagent reacting with a ketone or aldehyde, otherwise known as the Grignard reaction, where you form that special thing, another one of those. That's why I love ketones and aldehydes, because you can form carbon-carbon single bonds. This attacks the carbonyl carbon, forms a carbon-carbon single bond, and opens it up to an alcohol. The reason I'm putting this up is students get this wrong all the time. So I think I'd do one more practice with you. Maybe 2. And why don't you do this one for your fun and enjoyment? Anybody need more time? Are you guys done? Thumbs up. All right, looks like everybody's done. Let's do this. And here, what's different? Ooh, carbonyl with hydrogen and carbons. This is a aldehyde. Now, it could have been a ketone. What do I have up here? Ooh, a Grignard. Magnesium chloride on a carbon. Remember, X can be chlorine, bromine, or iodine. Second step, acid and water. Or if I put the water first and acid second, same thing. And now what happens? This attacks the carbonyl carbon, opens it up to an alcohol. What's attached to that carbon is still attached. And you made that special carbon-carbon single bond. Here's our double prime. Here's R prime. There's my R triple prime. Keep my eye on the carbonyl carbon. What's attached to it? H, which is R prime, CH3. This opens up to an alcohol. And what's my R group? 3 carbons. Which carbon has the Grignard? The end. And that's the molecule. Let's do one more, then I'll be finished for today with organic chemistry. I'll be playing with my back or being nice to it. And there you go. Your turn. What would be the organic product or product for the following? And hopefully you all see the whiteboard and see it on there. And when you're done, give me a knees up. Aren't you glad even when I'm in pain in my back, I still don't lose my sense of humor? Hope I never do. All right, anybody need more time? Nope, let's do it. Now we look over here and say, what? Ooh, an oxygen. And it's double bond to carbons. I have carbons here and carbons here. Remember, every bend in a line or ring is carbon, and this is a ketone. Ooh, what's different here? Carbon. Oh, magnesium halide. This is a Grignard reagent, where X can be chlorine, bromine, or iodide. In our case, it's iodine. Second step, well, acid, water. And this attacks the carbonyl carbon, but you know how violent organic chemists are. And what's attached to it is still attached to it. Opens it up to an alcohol, and you make that special, beautiful carbon-carbon, new carbon-carbon single bond. Well, here's my carbon. This one right here is this one right here. So what this tells me is I'll redraw it. What's attached to that carbon, including this methyl group, and here's that carbon. You don't have to draw it in. Then my R triple prime, oh, this one is a methyl group. And then this will be also an alcohol. And that's the molecule you get. And now I feel better because I've given you some more extra practice for test number 2. Now, before I leave, I don't know if you can see it here because it's black on black. I have my office chair. I got this the end of, right before class started this semester. Last year when I was doing physical therapy, my physical therapist said, you should get a better office chair because that may be part of your problem. And it turned out it was. This is called a steel case Leap office chair. It sells new for $800. And for a while, I didn't want to spend that money. And the reason I'm telling you this is, and if you need to know ever, somebody needs to know, there's this great place, I think it's in Oak Park, Illinois, not far, it's in the area, called Rework Furniture. And they had these on sale, or used ones, that were in beautiful condition for, what did I pay? $350, which is a lot less than $800. Plus they delivered, that was another $50, which was worth it. These things are heavier than all heck. This weighs, I bet, at least 200 pounds. But it's built like a tank. It's amazing what you can adjust on that. Not only the armrest, but the seat, how far forward or backward it goes. And then on your back part, it has a lumbar adjustment. And today I'm finding out how good it really is. And with that, Dr. White's going to say goodbye. I'll see you next Monday. I'll put out an email either Monday or Tuesday or Wednesday. We'll do the ketones and aldehydes practice problem set because we've finished a chapter. Boy, that means the semester's half gone. And with that, let's see if you have any questions or want to give me good wishes, like a thumbs up, hope your back's better. You don't have to, I'm just kidding. But I'm gonna say, oh, I have to. It's time to say goodbye, gehen gesund, be healthy. Back, gehen gesund too, I'm talking to you. And I will see you on Monday. If you need any help, I will have my office hour tonight. And bye.